No Vergence size-constancy by Paul Linton, City, University of London. When objects move forwards or backwards in space, the image they cast on the retina varies drastically in size. And yet, objects don't seem to change dramatically in size as they move closer or further away. One explanation is Vergence size-constancy. This is the suggestion that the visual system gauges the distance of objects using vergence, the angular rotation of the eyes, and scales the retinal image to cancel out these drastic changes. Evidence for this comes from the Taylor illusion, where the retinal image of the observer's hand is fixed using an afterimage. When the observer moves their physical hand closer, the afterimage appears to shrink, and when the observer moves their physical hand further away, the afterimage appears to expand. Sperandio and colleagues largely attribute this effect to vergence, as the eyes track the movement of the hand in darkness. The reason is that when vergence and the hand are moved in opposite directions, the illusion tracks vergence and is only marginally reduced in size. However, our recent work shows that vergence isn't an effective absolute distance cue once confounding cues have been controlled for. So, does vergence really affect perceived size? We tested this by increasing or decreasing the size of a target and asking participants to judge whether the target got bigger or smaller. At the same time, we increased the participants' vergence from 50 centimeters to 25 centimeters, and the question is whether this biased the results. There are two possibilities. If vergence doesn't affect perceived size, then there will be no bias and the point of subjective equality will go through zero. Subjects will be at chance in judging whether the target got bigger or smaller just when we didn't change the size of the target. But if increasing vergence from 50 centimeters to 25 centimeters really does reduce the perceived size of the target, then we will have to introduce a physical size change to cancel it out for participants to be at chance when judging whether the target got bigger or smaller. And given Sperandio and colleagues report something close to perfect size-constancy for their representative observer, this increase in physical size could be as much as 70 to 100%. However, our results indicate that vergence has no effect on perceived size for three reasons. First, we build a hierarchical Bayesian model from the data and find a non-statistically significant bias of minus 0.2%. Second, from a Bayesian perspective, we ran a JZS Bayes factor and found that the data were 4 times more likely under the null hypothesis that there is no Vergence size-constancy than under the alternative hypothesis that there is a small true effect. Third, from a frequentist perspective, even if there is a small true effect, it would be undetectable by even our most sensitive observer. So, for the purposes of an inferiority test, Vergence size-constancy is effectively zero. So we conclude that vergence has no effect on perceived size and draw 3 important implications. First, we need to reconsider our understanding of visual scale and realize that all of our visual cues to scale, accommodation, motion parallax, vertical disparities, and now vergence, all suffer from significant shortcomings. So, rather than the visual system being able to triangulate distance, we argue that visual scale is based solely on higher-level cognitive processes. Second, and related to this point, ever since Trotter and colleagues found that the large majority of neurons in the monkey V1 were responsive to changes in vergence, it has been supposed that this neural mechanism plays a central role in size-constancy. But our work suggests that size-constancy is completely due to top-down modulation from higher-order areas. Third, what are the implications for multisensory integration in the Taylor illusion? It now appears that rather than being a process of integrating the vergence signal with the hand signal, as suggested by Sperandio and colleagues, the Taylor illusion is a cognitive phenomenon that relies on participants having subjective knowledge about their changing hand and gaze position. A preprint of this paper is now available on bioRxiv, and please also see my British Machine Vision Association talk for further discussion of these results. Finally, I'd like to say thank you to everyone who helped with this project: Christopher Tyler, Simon Grant, Matteo Lisi, Josh Solomon, Salma Ahmed, and Chris Hull.